starting the recording a little bit late, just went through the announcements here. And then on Thursday, next Thursday, we have exam number 4, and that's it. And then it's summertime. And then you have final homework. I'm going to post that tomorrow sometime during the day, and that'll be your last homework. So that's it. Last 2 weeks are going to go super quick. It's going to fly by. Then I guess the only other announcement, just a quick plug, like I don't know if you guys have been getting the emails about the vaccines available on campus. So if you haven't gotten your vaccine shot, definitely schedule one of those and get that. But otherwise, anybody have any questions for me before I get started? No questions? Okay. Anybody get their vaccine shots yet? Good. Yeah. No. Oh, good. I'm glad to hear that people have gotten it. Yeah. I hope everybody. Oh, Matt, the second dose knocked me out. I'm also like an older man, yeah, it destroyed me. My wife, perfectly fine. She kind of made fun of me all day. But yeah, just, just if you have your second shot, just, sometimes it's not pleasant. Yeah. But, then I talk to people who are fine, just for me, lots of sleep. Yeah. I use it as an excuse to lay in bed and watch Netflix all day. I might've milked it a little bit, but yeah, I didn't feel too bad after my first either. Yeah. Yep. That's exactly it, Matt. Just aches and chills. Yep. That's what happened to me. Okay. All right. So this is just kind of a review of what we were talking about last class. Okay. And what we were talking about last class was the language of hypothesis testing. Okay. And basically what hypothesis testing is, just as like a quick refresher, it's a procedure based on sample evidence to test the validity of a claim. Okay. And so what I'm going to show you today is that exact procedure of hypothesis testing. And the good news is, the fantastic news is everybody take out your TI calculator. Doesn't matter if it's a TI-83 or a TI-84. I'm going to show you how to use your graphing calculator to make this super easy, to make it super, super easy. Okay. So the other thing that we were talking about here about hypothesis testing is, okay, so when you make a claim, okay, when you make a claim, it can be true or false. Okay, so just because you make a claim doesn't mean it's right. Okay, that's what I'm hitting at here. Okay, so hypothesis testing involves two statements. Okay, we have H sub 0. Okay, does anybody remember what I called this? It started with an N, if you look back in your notes. Dun, 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 dun. No takers? Searching. That's funny, Storm. Oh, man. I got you guys. So this right here was called the null hypothesis. Okay. And the thing about the null is it's assumed true. Okay. You start, think of your null hypothesis as your base assumption. Okay. And then we have H sub 1. Okay. H with the subscripted 1. And then followed by colon here. And this is what's called the alternative hypothesis. And what you're doing here is your alternative hypothesis. What you're doing is you're looking for evidence to support this. Okay, and if you guys remember, I had this example. Do you guys remember the criminal justice example, the justice system example I had last class?
Yes.
What was it? So like, what is the null hypothesis when you're put on trial? What do you assume? Defendant is innocent. Okay, that's your base assumption. And then the alternative here is, look, the defendant is guilty. He did it. He or she did it. Okay. And what you're doing here is you're looking to show evidence for this. So base assumption, and then the alternative is what you're looking to find evidence to support. And for as long as I've been teaching, okay, setting up the null and alternative hypothesis tends to be what gives students the most trouble. So we're going to spend a lot of time practicing that today, okay? Because actually, once you set up the null and alternative hypothesis, and once you set them up correctly in our course, like going forward and then actually computing a hypothesis test is actually pretty straightforward. Okay, is everyone okay if I go to the next slide?
I am. I'm good.
Good. Anybody else good? Okay. So then look, there were outcomes that we talked about for hypothesis testing. All right. So the language of hypothesis testing, when we conduct a hypothesis test, you can do one of two things. You can either reject the null hypothesis, or two, you can fail to reject the null hypothesis. Okay. If you reject a null hypothesis, what this means is evidence that you collect supports the alternative. Okay. So in our criminal justice system example, you know, the defendant is innocent or they're guilty. When you reject the null, this is what's going on. Okay. You're going to say, this is wrong. And you know what? The district attorney or the prosecuting attorney showed evidence that the person was guilty. Okay. So that's what rejecting the null means. It's our base assumption was wrong. The person is not innocent and they're guilty. When you fail to reject the null, what's going on is evidence does not support the alternative. All right. So going back to our criminal justice example. Right. When you fail to reject the null, what's going on here is you're saying, look, you know what, prosecuting attorney, you didn't show enough evidence to say that the person was guilty. Okay. So instead of, remember the terminology here, like even with the criminal justice system, right? They don't say like the person was 100% innocent. They say, look, they were found not guilty. You couldn't show evidence that they were guilty. And that's what's going on here when we say we failed to reject the null. It's like, look, you didn't show enough evidence to support your alternative. Okay. So we failed to reject the null. And what I'm going to show you in class today is later on is the process for determining how you reject or how you fail to reject a null. That's what we're going to focus on. Okay. Is everybody okay if I go to the next slide? All right. Let me ask you this, okay, before I go to the next slide. Okay, does our criminal justice system get it right all the time?
Not at all.
Not at all, right? Yeah. Okay. And what I mean by that is sometimes do innocent people get sent to jail, and sometimes are people who are really guilty get found not guilty. Like, does that happen every once in a while?
Yes, it does.
It sure does, right? It sure
Probably
does.
happening today.
It probably, you know what? I'm not going to comment, but they do make incorrect conclusions. You know, that's not to say that, you know, I do firmly believe that, you know, a criminal justice system gets it correct most of the time. You know, I do, but I do think they do make incorrect conclusions. Juries do every once in a while. Okay. So here's in statistics, you know, what is it? What do I mean? Like you make an incorrect conclusion. So because our conclusions are based on sample evidence, okay? Sample evidence, okay? There's always the possibility, okay? Of making an incorrect conclusion. Always, okay? You know, like sometimes when you collect a random sample, you just like the data you collect just doesn't do a good job accurately describing the population. And like that just, that happens, okay? So even though, I'm gonna go back for a second. So even though there are only two outcomes here, you can either reject or fail to reject, there's 4 possible things that could happen. Okay. And what I'm going to do when I say there are 4 possible things, there's going to be 2 things that are correct, 2 correct outcomes, and 2 incorrect outcomes. Okay. The first one is you reject the null when the alternative is true. Okay. This is a correct conclusion. Okay, that's very much akin to saying, hey, look, the defendant actually committed the crime, so we're going to find them guilty when they're really guilty. That's a correct conclusion. The other thing you can do is you can fail to reject the null. When the null is true. Okay, that's you find the defendant guilty when they actually are innocent. So like that's a good outcome. That's a correct outcome. Okay. Now let me walk you through what the incorrect conclusions are. Okay. You reject the null when the null is true. Okay. So when you reject the null, but the null is true, what's going on here is the person is really innocent. Okay. They didn't commit the crime, but the jury found them guilty. Okay. Is it really bad to send an innocent person to jail? Like, does that seem like a really bad outcome?
Yes.
Yeah, right. Like for example, if I was put on trial and they send me to jail, I'm gonna be honest with you guys, I wouldn't make it. All right. I don't have the constitution for that type of stuff. I wouldn't make it. Okay. So it's like bad. Okay. So this is an incorrect conclusion. Nobody found my joke funny.
No, I was laughing. I was.
Okay. You never know. I might be, might take charge of the prison. Who knows? You never know till you get there. But anyways, this is an incorrect conclusion. This is what's referred to as a type 1 error in hypothesis testing. Okay. And this is really bad. So what we do in hypothesis testing is we try to control for this error. So we're going to define something, okay? So we're going to have you guys seen me use alpha before in this class? The Greek
Yes.
letter. Yeah, I used it in confidence intervals. And does anybody remember what I defined alpha as? Or what Matt's like cheat was? Alpha is my willingness to be what? It's like how wrong. Okay, so alpha is like your willingness to be wrong. So what we're going to do is we're going to define alpha for hypothesis testing, and it's going to be equal to the probability of a type 1 error. Okay, this is also referred to as the test level of significance. Okay, and this is really important, level of significance. Okay. And so what we're going to do is, hypothesis testing is based on sample evidence. It also involves a probability. Okay. So we're going to set this probability and we're going to say, look, we don't want to send an innocent person to jail, but look, I know, I can't be 100% right in statistics every time because we're collecting sample evidence. So, how often am I willing to be wrong? So we're going to set this at either 1%, 5%, or 10%. Okay, the most common one is the middle one, 5%. And and when we start to get to examples of hypothesis testing, like when we start to get to problems, you're going to see me talk about level of significance. It's going to come up in the actual examples. Then the fourth outcome, you could fail to reject the null, when the alternative is true. Okay, this is an incorrect conclusion. Okay, so what happens in this case here is the jury finds the defendant not guilty, okay, when in reality they are guilty. So they really committed the crime, but I don't know, for whatever reason, they weren't able to show the best evidence, or they had a great lawyer or something. I don't know. Okay. This is called a type 2 error. We're not going to worry about type 2 errors, but if you were to take a more advanced class in statistics, they define this new variable beta as the probability of a type 2 error. And we're not going to worry about it, okay? For our class, okay? Okay, so the big thing takeaway here is we're going to be talking about level of significance, okay? So whenever you see the level of significance in our problems, when we get to them in a couple minutes, it's like, okay, I'm going to prime myself. That's my willingness to be wrong. Okay. And it's going to be a very small probability, very, very small probability. Okay. Is everybody okay if I go to the next slide? Everybody good? Everybody can still hear me, right? Okay. I hope so. All right. And trust me, like, this is just one of those times, and I know I say this a bunch. Actually, this might be the last time I say this. This is just one of those times when, you know, I throw the theory up there, and then once we get to the first example, it's like, okay, all right, I got it, Matt, I got it. So now what I want to talk about is setting up the null and alternative hypothesis. Okay, how you set up the null and alternative hypothesis. So this H0 and H1, how you set these up. So this is a, you know, it's a math class, right? Well, statistics class, but, you know, math class. And so what we're not going to do is we're not going to do hypothesis tests like innocent versus guilty. That's just not what we do. We want to put numbers to stuff. Okay, so that's what we're driving at here. You're going to put numbers to stuff. So there's 3 types of tests that we can have in this course. Okay. You can have what's called a left-tailed test. Okay. Then you can have what's called a right-tailed test. And then the third one, you can have what's called a two-tailed test. Okay. So a left-tailed test looks like this. Okay, you're going to have your null and your alternative statements, H0, H1. And your null statement here is going to be a statement of equality. It's that your parameter is equal to some number. And for a left-tailed test, what it is we're going to say, no way, the parameter that we're investigating is less than that number. Okay. And so when you do these problems, these numbers here, okay, are going to be the same value. And trust me, once you see the first problem, it'll make sense, okay? But there's going to be keywords in the problem that give away that it's a left-tailed test, okay? You're going to see things like, I think the value is less than this. I think it's decreased. Or I think it's gone down. Okay. Those keywords tell us that it's going to be a left-tailed test. Now, right-tailed test is the opposite of this. Okay. It's the parameter is equal to a number. And then what we're investigating, all alternative, is, wait a second, no way. The parameter that we're investigating, either the mean or proportion, it's greater than that number. Okay. So we do a left-tailed test is less than, a right-tailed test is greater than. So the keywords here is that it's more than, that it's increased, or that the number's gone up. Okay, so those type of words are going to give away that it's a right-tailed test. Okay, so a left-tailed test is less than, a right-tailed test is greater than. Does anybody have a guess what a two-tailed test is then?
Equal.
So H1, you're close. You're close. So notice that the null hypothesis is always a statement of equal. Okay. So close by, and I understand the thought process. The alternative here is that it's not equal to that number. Okay. So the key words for this type of test is that, hey, no way, the parameter is different from that value, or that the value has changed over time. Okay. So two-tailed tests happen when like you're unsure if a number over time, all right, has gone up or down. Okay, like suppose you wanted to investigate mean charitable giving, do you guys think that mean charitable giving on people's taxes over the last year has gone up or gone down?
I'll say up.
Maybe, right? Like some people are staying at home, they're not spending any money. So maybe it's gone up because people have more money, because they aren't spending it on vacation and stuff. But then also maybe it's gone down, right? Because a lot of people lost their job because of COVID. So I don't know, So this is a case where you just want to investigate if the number has changed. That's all. Okay, so keep these in mind. Left-tailed, right-tailed, two-tailed. And I have 5 examples in this slides, and we're going to do at least one of each of these. So you'll get to see how it's all set up. Okay. Actually, the first 3 examples are going to be one of each, so that you get a good way to see this. All right. Everybody okay if I go to the next slide?
1 second.
Sure. Yeah.
All set.
Okay. All right, so there's actually 2 methods for hypothesis testing. Okay, there's one that's called the critical value approach. And then there's something called the p-value approach. Okay, this is the method we're going to learn in our class. All right. The reason there's a couple reasons why I teach the p-value approach to hypothesis testing. So if you ever end up using statistics in the real world or in your future studies, like hypothesis testing is done primarily using the p-value approach. So it's more useful that way. Also, because we're in the remote environment, I really like to rely heavily on our graphing calculators, just because, it's not the easiest thing learning remotely, so I try to make it a little bit less stressful on you guys. And I hope you guys like using the graphing calculator at least. So your graphing calculator does the p-value approach here. It's going to give you the p-value. And I'll talk about what a p-value is in a second. And so also, like, if you end up ever using statistics in in whatever career path you go down, you'll always use p-values. Okay. All right. So here are the hypothesis tests we're going to do. We're going to do a hypothesis test for a mean. So for mean mu, and this is when sigma is known, just like we did for confidence intervals. Then we're going to do hypothesis testing for mu when sigma is unknown. All right. And then the last thing we're going to do is hypothesis testing for a proportion. Okay. And again, we're going to rely very heavily on the TI calculator. and it's going to be awesome. And then we are done. Okay. Everybody okay if I go start the next few slides? Dun, 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 dun.
Yes.
Okay, so what is the P?
Say that again. Someone
What
just
is the
spoke.
P? The last one you.
For proportion. This is a proportion.
Thank you.
Mm-hmm. Okay. So here we are now. Hypothesis testing for a mean. Okay, so this is for the Greek letter mu for a mean. Okay, when for sigma, okay, that's the Greek letter sigma, the population standard deviation is known. Okay. And what we're going to use is this thing called a p-value. So in statistics, the p-value is the probability, so it's a probability of obtaining results as extreme as the observed results of a statistical hypothesis test, assuming that the null hypothesis is correct. Okay. So what does this mean? Right? The p-value looks at, so what you're going to do is this is just for a mean. What you're going to do is you're going to collect a sample. And look at X bar. Okay. Like, let me give you an example. Suppose I'm interested. Let me back up a little bit. On average, what do they say people should get? How many hours of sleep should people get a night on average? What do I'm going to put in quotations. What do they say? Someone just said it, and in the chat there, yeah, they say like on average you should get 8 hours of sleep. Okay, I'll tell you this: I don't know when the last time I got 8 hours of sleep was. Okay,
Same.
yeah, right. You know what?
I feel so nocturnal right now. I just got to find which animal I am. I might feel like I'm a bat.
I hear bat. Oh man. I used to, I'm just going to go out a little bit tangent here, but like when the lockdown first started and my wife and I were at home, we used to stay before our son was born. We used to stay up till like 2-3 o'clock at night every night and then sleep till like 9-10. It was glorious. I don't know why I felt like sharing that with you guys, but I don't know if anybody else had a similar experience.
Oh, it's only great times you always share with us, and we love that.
Say that again.
It's only great times you always share with us, so we love that.
Thanks. You know what? I can collectively see through the computer screen the other, everyone else in the class rolling their eyes. Okay, but anyways, so suppose you were interested in seeing do you guys think college students in general get more or less sleep than 8 hours a night?
Less.
Do you think they get less? Oh, sure. I agree. What is sleep? Yeah, you guys it's so, you know what? Look, being a college student's hard. I'm gonna be honest with you. It's not the easiest thing. I remember. So you're juggling a lot. Okay. But so here's what we might want to do with the hypothesis test. We might want to test to see if, look, on average, do college students get less sleep than 8 hours a night? So if you were to take a random sample and you talk to 100 college students and you found out that on average they get 7.8 hours of sleep a night. Is that really far from 8?
Nope.
No. Like that might not be enough evidence to show that you guys get less than 8 hours of sleep on average. But imagine you did this and you computed the value 6.5. Okay, is that pretty far away from 8 hours of sleep?
Relative, yes.
It's relative, but yeah, like there's a big difference between getting 8 hours and 6.5 hours of sleep. Yeah. So like what a p-value does is it looks at values like this in this, and it says, look, you should be getting 8. So let me compute the probability that if you do get, if the null were true and college students did get 8 hours of sleep, what is the probability if I repeated this experiment and get a value worse than 6.5? Okay. And basically what you need to know for a p-value is this. When a p-value, which is the probability, is low, okay? And generally what that means is it's less than, 5%, 1%, okay? The results are statistically significant. And what that means is when results are statistically significant, our assumptions are most likely incorrect. And if you think about hypothesis testing, and I'm going to go back real quick, our assumptions, the null hypothesis is where you make your assumption. So when the p-value is low, our null hypothesis, our assumption is most likely incorrect. And what that means is we've now found evidence to support our alternative. Okay. So how do you, is it okay if I go to the next slide? And I'm going to show you how to look at the p-value and everything in our first example. And I promise you, it's like really easy. It's not that bad. I promise. I promise. I know everyone's like, Matt, what are you talking about? Statistically significant. Like, just trust me. Once I get to the first example, boom, it'd be easy. Okay. So how do we use this p-value? And the good news is our calculator will give it to us. So you compare this p-value to the level of significance of a test. And remember, that was my alpha, okay? So if the p-value is less than the level of significance, okay? Whenever p-value is less than alpha, you reject the null, okay? If the p-value is greater than the level of significance, you fail to reject the null, okay? And I have this silly saying to help me remember it. When the p-value is low, the null must go, so you reject the null. And when the p-value is high, the null must fly, so you fail to reject the null, okay? So just remember, when the p-value is low, the null must go, and the rest kind of falls into place. Okay. Anybody okay if I just walk through the next steps, and then we'll do what I want to do is I want to show you the procedure. We'll do one example, then we'll take our break, and then we'll come back and we'll just do more examples. Okay. When you do these problems, these hypothesis testing problems, okay, there's a 5-step process, okay, for testing for a mean, sigma known. This is using the p-value approach, okay? So when you go to do your final homework, which I'll post tomorrow, you're going to want to show these 5 steps, okay? And what's really good is your calculator is going to do a couple of the steps for you, but you still need to walk through all of them, okay? So step 1 involves 2 parts. The first thing you're going to do is you're going to define the parameter. Okay, and what this is the parameter you're investigating. Okay, and it's going to be literally be something like this. We're going to let mu be equal to the mean and then whatever the context of the problem is. Okay. And then step 2, you're going to have to set up the test or the second part of step 1, excuse me. Okay. So what that means is you're going to have to decide if it's a left-tailed test So your null will be that the mean is equal to some number, and you're saying, no way, I think the mean is less than that number. Or if it's a right-tailed test, so you're going to start with the mean is equal to a number, and then the alternative is, wait a second, no way, the mean is greater than that number. Or you're going to have a two-tailed test, where its mean is equal to a number, and the alternative is, wait a second, no way, the mean is different, it's changed, it's no longer equal to that number. Right? And trust me, once you see the calculator, if you can set the test up correctly, the rest of it just boop, 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 falls into place. Okay, it's not bad. Okay, this is, trust me when I say like this, you know, if you can figure this out, how to set up the test correctly, boom, you're going to be great. Step 2 is you're going to select the test level of significance. This will be given in the problem. And it's just going to be alpha is equal to something. Okay. Usually it's going to be 5%, 0.05, but we might change it a little bit. Then the next thing you're going to do is you're going to compute what's called the test statistic. And all this is, literally all this is a z-score. Okay. And that's, you know, basically a p-value is you compute the probability using the z-score that you calculated. Okay. And then that's why we spent all that time learning how to do that. Okay. Just so you understand what's going on behind the scenes with the p-value. But it's just the z-score. This is, boom, z-score. X bar is the sample mean. This mu with a subscripted 0 is the assumed mean. And it comes from the null. So like whatever number you put up here in the null hypothesis, that's the value that goes here. Sigma is the population standard deviation. And n is the sample size. Okay, step 4, the next thing you're going to do is you're going to find the p-value. Okay, and for this, you're going to use your TI calculator. And there's going to be more on this in the coming slides. Okay, and it's actually like, oh my gosh, it's so easy. So easy to use the graphing calculator. And then once you get your p-value, okay, it's just going to be a probability. So the p-value is going to be somewhere between 0 and 1. Excuse me. Then you're just going to make your final conclusion. Okay. So if the p-value is less than the level of significance, you reject the null. If the p-value is greater than the level of significance, you fail to reject the null. All right. Does anybody feel like they're drinking from a fire hydrant right now with all this? You guys get that feeling where it's just like, Matt, gosh, this is kind of like crazy right now. I'm not sure I fully understand.
I've already drowned.
You've already, listen to me, And I know I say this all the time. Like, you got to let me get the theory. And then like, as soon as we do our first example, I hope that you guys all feel like after I do the first example, it's like, oh, okay, yes, I got it. This makes sense. I can follow the procedure now. You know, that's my hope that you guys feel that way. And that's exactly what's going to happen when we get to the first couple examples. I promise you. Okay. So actually, we're going to do it a little bit differently. This is a good place to take a break, and then we'll come back and we'll do our examples. Come on. All right, so let's take our break and let's be back at 2 p.m. Okay, we'll take a 11-minute break here. Okay. And then when we come back, all we're going to do for the remaining 50 minutes is just examples. Example to have this make sense. All right, so everybody enjoy their break, and I'll see you in about 10 minutes. But before I go, any last minute questions? Okay. All right, enjoy your break. I'll see you at 2. All right, everybody. Just checking my mic again. Can everybody hear me okay?
Loud and clear.
Okay. So what you want to do for the next 3 examples we have of class, take your TI calculator out. It literally doesn't matter if you have the TI-83 or TI-84. In this case, they're both the same, okay? So if you grab your trusty calculator here, okay, and you press the stat button on your calculator here, and you scroll over to tests. Do you see the first 2 things here, something called z-test and t-test? Does everybody see that on your calculator?
Correct. So I guessing like it's these scores, so we'd be pressing number 1.
Yep. So here's the deal. That's exactly right. Number 1 here, z-test. This one right here, you use when you do hypothesis tests for a mean. When sigma is known. And that was perfect how you just put it. Was like, we use the z because we're computing a z-score here. That's exactly where it comes from, okay? So it's going to be option number 1 on your calculator. When you load up your option number 1, there's going to be 2 things you'll see here. It's going to say input when you have your data, or input when you have your stats, okay? For these example here, we're going to be using stats, okay? When next class, we'll probably get to using data, but for this one, we're going to be using the stats option right here. And I'm going to explain all of this stuff that you put in, so don't even stress about it right now. All right. So let's just jump right in. We're probably only going to get through 3 examples here, and then we'll save the t-test for class next time. Okay. Dun, 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 dun. You guys ready? Everybody ready for the first example? Yay, nay? I hope everyone's, you guys can all hear me, right? Yeah, okay.
Yeah.
Let's do our first example. So this is about Netflix, okay? Which kept me up a while last night. Anybody ever get down a Netflix hole? Keeps you up all night? I'm sure we all have. Okay, so here's the problem. A study conducted in 2015, all right, by this technology company, Ravi, I'm not sure, but it's now called TiVo, okay, showed that the mean time spent per day browsing the video service for something to watch was 19.3 minutes. Okay, so this was the mean in 2015. Okay, which I thought is crazy, right? Like people are like, oh, I want to go watch something on Netflix, and then they spend like 19 minutes browsing before they find something to watch. Okay, just interesting, right? Just like I don't know why I find that really interesting, because you know what, I'm guilty of that. Sometimes I'll be like, oh, I have 45 minutes to watch something, and then I'll browse for 30 minutes and be like, well, gosh darn it, I can't watch anything because I spent all my time browsing. So what happens? Next, it says assume the standard deviation for time spent looking for something to watch on Netflix is 8 minutes. Okay, so here this standard deviation is 8 minutes. Here you're given sigma is 8 minutes. Okay, so again, they're giving you the population standard deviation. Okay, so a social scientist is interested, a little bit of a typo, to know whether the mean time spent browsing Netflix has increased. Okay, so for whatever reason, this social scientist wants to know that it's increased. So suppose the social scientist it takes a random sample of 50 people. So this 50 here, okay, that's my sample size. And the mean time they spent browsing Netflix was found to be 21.5 minutes. So that's my sample mean. Okay. So now here's the next thing. At the 0.05 level of significance, look, level of significance. So this right here is my alpha. Is there evidence to suggest that the mean time spent browsing Netflix has increased from the 2015 level? Okay. So look, here's the deal. Is 21.5 minutes, is it obviously greater than 19.3 minutes? What do you think? Is it greater than?
No.
Yeah, no, hold on. Like, yeah, like the 21.5 is greater than 19.3, right? But
Yeah.
like, that's just a random sample of 50 people. So what we want to investigate is like, look, is this X bar from the 50 people? Is it provide evidence to suggest that, wow, people are spending more time on average browsing Netflix? Okay, that's what we want to investigate. So here's what we need to do as a group.
Professor, I'm sorry to interrupt, but I don't just understand your last statement. What? Oh, if it is a question.
What do you mean? Is it a question?
I really don't understand the last sentences you were saying.
Is there
about
evidence?
the 21.5?
Gotcha. So like the 21.5 is just a random a sample mean from a random sample. Okay. So what we want to investigate is, look, this 21.5 is definitely greater than 19.3.
Oh, thank you. I got it.
But this is just from a random sample. So does it provide enough evidence for us to say that nowadays people are definitely browsing Netflix more? So that's what we need to investigate. So here's what's going on. This is where it gets hard. Like, none of the math that we're going to do in this section is difficult at all. But what we have to do is we have to take these jumbled numbers here and fit it into these 5 steps. That's the hardest part here. Okay. So let's do that. Okay. So is everybody okay if I go to the next slide so we can go through the 5 steps together? All right. And so for this first one here, awesome. So for this first one here, I'm going to do most of the heavy lifting. And then as we get to the next 2 examples, I really would like some people to chime in and help a little. Okay. Okay. So the first thing you have to do is you have to define the parameter. Okay. So look, mean time spent, that's what we're investigating. So define the parameter. I'm going to let the mean, be the mean time spent browsing Netflix. Okay. Now here's the thing. I know what it was in 2015. Okay. So I want to see if it's increased since then. So I'm looking at the mean time spent browsing Netflix now in 2021. Okay. Because again, I know what it was in 2015. All right. And now I want to see if it's gone up since then. So in 2021. All right. So the next thing I need to do is I need to set up the test. All right. And I'm going to go back a slide here. Okay. Do you guys remember in the previous slides, I said there was like keywords that gave away the test? Does anybody know what the keyword is in here that tells me what type of test this is going to be? If it's right-tailed, left-tailed, two-tailed? It's absolutely going to be a right-tailed test, but like, what's the keyword that tells me you're right about that? Yeah. Yep. Awesome. You guys got it there. Increased. That's the keyword that tells me it's a right-tailed test. Okay, so a right-tailed test is this. It's going to be mu is equal to a number And we're going to say, no way, mu is greater than that number. Okay, so we have to figure out what number to put there. So here's the deal. We know what it was in 2015. It was 19.3 minutes. Does everybody see that? It was 19.3 minutes in 2015. So what we want to do is we want to show evidence that it's increased since then. Okay. So here's the deal. I don't know for sure if it has or hasn't increased. Okay, from this 19.3 minutes. Okay. So we're going to start with the assumption, okay, that it is still 19.3 minutes. And remember, here's what we wanted to do. We wanted to show evidence to suggest that it's increased from this level. So what we're looking to show evidence for is no way, it's greater than 19.3 minutes. There's just so much on Netflix. Okay. So that's, I know it seems weird, but like that's the hardest part there, like setting that up. Once you set that up, the rest of it just is going to fall right into place. Okay. So base assumption. So we start with the assumption that it's still the same as 2015. And looking here, we're going to show evidence, or hopefully, let's see, look for evidence to say it's increase. Okay. The next thing we have to do, step 2, is select the level of significance. What is the level of significance given here? What is it? Bum, 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 bum. You guys see it right here? 0.05. Yep, that's my level of significance. Okay, and this is important because we're going to compare this to p-value. Okay, we're going to compare this to the p-value. All right, we're going to do this next, compute the test statistic, this z-score by hand. Okay, and then I'm going to actually show you that it just pops up on the calculator. But let me show you where it comes from here. Okay. So you're going to take your X bar, your sample mean, which you found to be 21.5 minutes. And you're going to subtract mu sub 0. That's where it comes from the null, this 19.3. Sigma, it said, it gave you the standard deviation was 8 minutes. And they talked to 50 people who watch Netflix. Okay, so watch me do this in my calculator here. So I'm going to take 21.5. I'm going to subtract 19.3. Then I'm going to divide by 8 divided by the square root of 50. You have to put both the numerator and denominator in parentheses. That's really important. Okay, really super important. And you should get this. Okay. So 1.9445 or 1.945 when I round it. 1.945. No, I'll just go 445. Okay. So what we're next going to do is we're next going to compute the p-value. Right. Please take out your calculator and follow along with me on this. Okay. It's super important because this is how you're going to do your homework. You're going to do the last exam. So it's just like you need to follow along with me on this one. All right, so everybody hit the stat button. And then you're going to scroll over till you get to tests. Okay. And what number was it that I said that we were going to use?
The first one?
Yep, z-test. Yep. Boom. So under number 1, you're just going to hit enter. And then everybody scroll over till you see stats. Okay, so whenever you're given the summary statistics, okay, and not the raw data, you're going to use stats. All right, now watch this. And then scroll down. Mu sub 0. That comes from, look, mu sub 0. That comes from the null. So you're going to put 19.3. Sigma is the standard deviation. Look, they told us in the problem it was 8. X bar, right? Look, X bar, the sample mean was 21.5. So I'm going to put that as X in X bar. N, okay, how many students, or not students, how many people did we sample for this problem?
50.
50. Yes, I'm going to put in 50. And then look here. Do you see these things here? The not equal, less than, greater than. This is going to match your alternative. So my alternative is a greater than sign. So I'm going to scroll down here, and I'm going to have to scroll over to greater than to match my alternative. Hit enter. So it's now flashing over here. And now let's scroll down till you hit calculate. Okay, so everybody on your calculator, make sure you have these exact same things that I have. Okay. And then how many people got this right here? How many people see this on their screen? I got Alexandra, great. Anybody else? Storm, Melissa, awesome. I do. Great. Look, and this is what's awesome. Okay. First off, compute your test statistic. When we did it by hand, or when I did it by hand, I got 1.9445. So this Z output right here, that's your test statistic. Okay. So you no longer even need to do that by hand. Your calculator will give it to you. This P under it, that's the P value. Okay. So it's 0.0259, 0.0259. Okay. All right, so that's, I guess what I'm trying to hint at here is like the calculator, was it, I'm just got to stop stuttering, but like, was the calculator pretty easy to use here? Like, did it not seem that difficult? Like, would you guys agree that the calculator, always, like what is always hard for these problems, and I think I said this, that's the best thing ever invented. Yeah. Like, I think what's always hard is just figuring out like how to set up the problem. You know, that's the hardest thing. Like once you figure that out, it's like boom, 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 boom. Okay. But now we still need to make a conclusion. Okay. So what you're going to do is you're going to take your p-value and you're going to compare it to the level of significance. So is my p-value less than this or greater than this? Is 0.0259 greater than or less than 0.05? Yeah, it's less than. Okay, so since the p-value is less than level of significance, so look, now you're just going to go back and look at your, what do we do? If the p-value is less than the level of significance, that's the first thing we have. Boom, we reject the null hypothesis. Okay, so what that means when we reject the null is we're saying we do not believe this, and we have evidence to support all alternative. So to put this into some verbiage, what this means is evidence does suggest the mean time browsing Netflix has increased, because that's what we were testing. Look, we were testing to see if it's increased, has increased from the 2015 levels. And what's really important to know, what I'm not saying, this is so important. What I'm not saying is the new value is 21.5 minutes. That's not what I'm saying, okay? Because that's just the mean from 50 people, okay? I'm not saying it's 21.5 minutes. I'm just saying, look, it's not 19.3 anymore. It's definitely gone up. I don't know what the real value is, but it has definitely gone up. It's definitely increased. Boom, it's increased. All right, so at least the first example, was it not the worst thing in the world here?
Wasn't too bad. I feel like it just needs a lot of work as usual.
Yep. Would you guys agree? Just like the math is not hard. The calculator is not hard. It's just like setting it up. That's the hard part. Yep, totally less scary than it seems. I agree. Okay. And again, this was only the first one. So let's do at least, let's try to get 2 more in with the time we have left with class today. Okay. You guys okay if I go to the next slide? All right. Boom, boom, boom. Let's do this one here. So according to the most recent general social survey, all right, college students watch an average of 2.5 hours of TV per day. Okay, so this is what the general social survey by the NORC, National Opinion Research Council, out of the University of Chicago says. Okay. So a certain statistics professor at WCC believe that students, so many typos here, believes that students at WCC watch less than 2.5 hours of TV per day on average. Okay. So look, this 2.5 hours, this is the general average of all college students. A certain statistics professor, let's even just assume that's me, okay? I think WCC students watch less than 2.5 hours of TV per day on average. Okay, what is the key word in there that tells me what type of test this is going to be?
Less than. Oh,
yeah, less than. Boom, right here. So when you see this keyword less than, okay, is it going to be right-tailed, left-tailed, two-tailed?
Left.
Yep, boom, left-tailed. You can see how it's starting to fall into place here. I know it's going to be a left-tailed test. All right, to test his claim, he samples 30 WCC students. Okay, so that's my sample size, boom, right there. And finds the mean hours of TV watched per day to be 2.35, okay? So this is my sample mean, okay? Next, it says, assume the standard deviation for hours of TV watched per day is 1.75. So that's my sigma. At the 0.05 level of significance, boom, right there, that's my alpha. Is there evidence to suggest that WCC students watch less than 2.5 hours of TV per day on average? Okay. So all you have to do again is take this information, okay, and figure out how to walk through the 5 steps, okay? And let's see if you guys watch less TV on average. I don't know, you know? All right, is everyone okay if I go to the next slide? Boom, 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 boom. Boom, boom. So generally, as I go through this, honestly, I think step one is the hardest part. And then once you figure out the intricacies to setting up step one, it's like, whew, it's just going to fall into place. Okay. So we have to define the parameter. So again, this is let mu equal to something. It's the mean what, okay? So can anybody tell me what we're investigating, okay? Mean hours of TV watched per day by who specifically are we investigating for? And I'll go back. Not you see here you have to be more specific. It's not college, not just college students. Which college students? This is where you get yeah. See, like I know what the average is of all college students. It's 2.5. Okay. But I'm specifically, you have to be very specific here. I am like specific about WCC students. So it's the mean hours of TV watched per day. By WCC students. Okay. And then look, we recognize the keywords. Sorry, like my stutter's a little bad today. We recognize the keywords here less than. Okay, so it's going to be a left tail test. So it's mu is equal to something, and the alternative is that no way mu is less than something. Okay. So what assumption, what number are we going to start with, assuming WCC students watch? And then no, it's like, no way, I want to show evidence it's less than that number. Yeah, exactly right there in the chat. Thank you. And look, you can see it here. I want to show that it's less than 2.5. Okay. So I want to show evidence that that mu, the mean hours of TV watched per day by WCC students, is less than 2.5 hours. So you have to, if you want to test to show evidence that it's less than 2.5, you have to start with some assumption. So we'll start with the assumption, okay, that you guys, WCC students, watch the same as all other college students. Okay. Boom. Right there. And then once you get this set up, once this is set up, okay, the rest you're going to notice we're going to go right to our calculator and it's going to be like boom, 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 boom. So level of significance is 0.05. And now when it says compute the test statistic and the p-value, you can actually just use your TI calculator. So everybody grab the trusty calculator. So hit the stat button. You're going to scroll over to tests. Boom, 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 right here. And what was the option again? I forgot. Yep. Thank you, Alexandra. Yep. Option number 1, Z. All right. So you're going to go to option number 1. And again, you should see stats still highlighted here. So what's going to happen is your previous problem is saved in there. So we have to go through and edit it. So scroll down. Mu sub 0 comes from the null. So it's 2.5. Sigma is the standard deviation. So I'm going to have to scroll back here. I was told that was 1.75. X bar was the sample mean. Here it's 2.35. And then N is my sample size. So how many college students, WCC students, did I sample here?
30.
And then look, you have to go back and you have to make sure that this matches the alternative, which is less than. So I'm going to go over to the less than. I'm going to hit enter. Okay. So then you're just going to scroll down next to calculate. Okay. So once you hit calculate, just hit enter. And how many people see this value right here? See what I have on the screen here. Alexandra's got it. Great. Anybody else got this too? Bertha, thank you. Thank you very much. Awesome. I appreciate it. So look, your calculator so here's basically what's going on. Your calculator solved the problem for you. You just need to interpret the results now. That's really what's going on here. Okay. So this first thing, Z, is the test statistic. So it's negative 0.4695. So negative, it's okay to be negative here. Not like a negative person, you know what I mean, but just like it's negative value. So negative 0.4695. Oh my God, I just said it. I can't even remember it. 4695. Then the p-value here is equal to, and it's this p here. P is 0.3194, 3194. Okay. So the last step is the conclusion here. Okay. Is the p-value, is that p-value greater than 0.05? Would you guys agree that 0.3194 is greater than 0.05? Yep, totally. So p-value is greater. So let's go back. What do my conclusions mean? If the p-value is greater than the level of significance, fail to reject the null. So since p-value is greater than level of significance, we fail to reject the null. Okay, so what that means when we fail to reject the null is, hey, look, evidence did not suggest that you guys watch less than 2.5 hours of TV per day. So evidence does not suggest WCC students watch less than 2.5 hours of TV a day on average. So it looks like we all still find time to watch our shows. And I get it. You know what? There's just so much good TV on. I can't help it. All right. So what do you think? So we've done one reject. We've done one fail to reject. It's really like, and I'm just curious in the chat, would you guys agree that like the hard part is number one, setting it up and then making sure in step 5 you do the right conclusion? Like, would you guys agree that those are really the tricky parts here? Yeah. And here's the thing, literally all we're going to do Thursday and most of next Tuesday is just practice this more and more and more and more. And the more examples you see, I promise you, the easier it's going to get. I promise. Okay. Everybody okay if I go to the last problem, last example we're going to do today? Let's do it, huh? Sound good? I hope everyone's still paying attention. All right. Here's the last problem, okay? And then we'll get through this and we'll call it quits. So at a large company, the attitude of workers are regularly measured with a standardized test. So basically what's going on here at this company, they're giving them a standardized test, okay? And they just ask questions and it just measures their attitudes about their jobs. All right, so the scores on the test range from 0 to 100, with higher scores indicating greater satisfaction with their jobs, okay? So the mean score over all the company's employees was 74, okay? So they gave this to all the employees and they found out it was 74, okay? So that's the mean of all employees. And then what's going on here with the standard deviation of 8. So you're given sigma. Okay. So this slide was obviously made pre-COVID because now everyone's telecommuting. But anyway, so some time ago, the company adopted a policy of telecommuting. So under the policy, workers could spend 1 day per week working from home, which is, sweet. Although it makes me, in the time of COVID, I don't know if I work from home or live at work sometimes, But anyways, after the policy has been in place some time, okay, a random sample of 80 workers was given the test, okay? So this is my N, to determine whether their mean level of satisfaction has changed since the policy has gone into effect. So it turns out that the sample mean was now 76, okay? So from the 80 people, this is the new sample mean. Using this sample at the 0.05 level of significance, so this is my alpha, again it's 0.05. Can we conclude the mean level of satisfaction is different since the policy change went into effect? Okay. All right, so first off, is there any keyword in here that tells me, what type of test this is going to be? What do you guys think? Are there any keywords in here that give it away?
Greater?
I don't see a greater than in here, right? So right there, perfect. Look, changed. Different. So I know 76 is greater than 74, but then I think that's where you were going with what you were suggesting. We want to see if it's changed, okay? So what type of test is this? And I gave you those keywords, what type of test is this? It's not right-tailed, not left-tailed. Yep, it's a two-tailed test. That's why it's super important to look through and I literally how I do right here on this slides, circle the keywords. So it's changed, it's different. Matt told me that's two-tailed. Hopefully you don't use that voice. I don't know why I made that voice, but okay. So now all you have to do is take this information and put it into the 5 steps. Okay. Okay, so step 1, define the parameter. So we're investigating something. It's the mean what? What are we investigating here? Let me go back. Mean level of satisfaction after what has happened. Yep, perfect right there. Since telecommuting, since this new policy, the new policy of telecommuting. okay? And we said it was two-tailed. So it's mu is equal to something versus no way, it's no longer equal to that number. Well, look, we want to see if it's different since the policy change has gone into effect, okay? So what was it before the policy change went into effect? What was this mean satisfaction score on the test? I'll go back. What was it before telecommuting? Perfect, right there. Yeah, it was 74. Yeah. So look, we're going to start with the assumption that it's still the same. And what we want to show evidence for is no way, it's changed. Okay, it's no longer 74. All right, we all like working from home. You know, I like working from home. I get to hang out with my wife, go for a walk whenever I want, like, you know. But then there's some people who are like, I'm so sick of being in my house, I want to get out, you know. So like, I don't know. So we want to see if it's changed. So the level of significance, again, it's 0.05, it's given. So again, test statistic and p-value, you're going to jump right to the calculator. So again, you're going to press your stat button. You're going to go over to tests, and it's option number 1 here. So it's stats. And now what you're going to do is you're going to go through and you're going to change things. Okay, so H sub 0 is 74. The standard deviation, if you look back at the problem, it was given to you, it was 8. The new sample mean, look, sample mean was 76. N is the sample size, random sample of 80 workers right here. And then you just have to make sure that you match the alternative here. So the alternative was not equal to. So right here, boom. So then we're going to scroll down to calculate. Right here, calculate. How many people have this on the screen right here? Storm, perfect. Anybody else?
I have a different P. My P is 0.987.
You probably, what's going on if you look back, you probably still have it as this one right here.
Yes.
Yeah. So you just have to make sure it's this.
Thank you.
Yep. Anybody else get this? So Storm, Alexander, perfect. Okay, so my z-score is 2.2361 when I round it to 4 decimal places. And my p-value was 0.0253. All right. What are we doing? Are we rejecting or failing to reject? Bum, 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 bum. What do we think? P-value is less than alpha. Yep, since p-value is less than the level of significance, we reject the null. Boom, you're gone. So what we're saying here is evidence does suggest, yeah. The mean level of satisfaction has changed since the new policy. And there you go. So you have all just done your first 3 hypothesis tests. All right. So what we're going to do next class, we're going to spend the first hour of class doing hypothesis testing for a mean when sigma is unknown. Also super easy. And then we'll start hypothesis testing for proportions. I'm going to put up a new PowerPoint slide tomorrow with your homework for everything. And I'll shoot you an email when it's all done. Okay. That's it, everybody. I'm going to stop the recording.